Next up, we've got Josh Clarke with Destiny Copper.
My name is Josh Clarke. I'm the lead scientist at Destiny Copper. Just to take you guys through some of the work we're doing here and support in part through Mika. Destiny Copper has developed a patented copper extraction clean tech. So essentially, anytime copper is in solution, we have a very low GHG, very low energy method to recover it as a pure metal. Now, the technology is characterized by these four main pillars. We are a low energy process. The technology is rapid in the way that we can dramatically remove high volumes of copper from solution. It's a low capex solution. As you can see, our pilot plant is essentially tanks and pumps. We aren't inputting electricity or heat to recover the copper. It's a spontaneous chemical reaction that can also recover copper from waste. So mining waste, industrial waste, characterized by the production of electroplating operations or semiconductor manufacturing. They generate very high copper-rich acidic waste streams. Typically, these are just incinerated in traditional manufacturing. So we're able actually to recover these, what would have otherwise been incinerated copper materials. So we're not a primary copper producer, but really a secondary way to introduce copper into the supply chain. Traditional copper manufacturing is expensive, energy intensive, in some ways inefficient, and there's negative environmental impacts associated with it. Through our process to recover copper from waste, we hope to alleviate some of these concerns. Now, the chemistry, I won't get too far into the technical slides here, but it's really a simple chemical metal exchange that we're augmenting. These metal exchange reactions between iron and copper have been known since antiquity. I think the ancient Greeks used to think as well that they were performing alchemy when they would put a piece of iron into a copper-rich solution and it would get covered in a layer of copper. It's not alchemy, it's chemistry. And there was scaled up in China as well as in Europe for the production of a very impure copper. These reactions were also scaled in the southwestern United States. This was a surprising stat to me, but 25% of all copper in the United States in the 1960s was produced via these metal exchange cementation reactions. However, they were very impure copper products. About 20% by weight was iron and other impurities, and you only had an 80% or so pure copper. That had to go to very high energy intensive refining processes, which kind of negated the low energy spontaneous chemistry of a cementation reaction. So the Destiny process is an innovative chemical treatment that yields a high purity copper through these exchanges. And I think best way to show you how this works is to take you into the lab, show you two side-by-side beakers here. On the right, you have the copper-rich solution with the blend of Destiny additives dissolved alongside the copper. And on the left, you have a beaker with just copper sulfate. Piece of identical scrap iron in both of these beakers. And within minutes, you can really see a dramatic difference in the way the copper reacts with the iron. On the right, you have granulization and a weak adherence of the copper to the iron metal surface. On the left, you have a sheet of copper, which basically passivates that iron. So after an immediate plating of copper, there's no more turnover of this chemistry. And you can see just how lightly that copper adheres on the right. It actually falls off just really from its own weight. And then we don't have to really put a lot of energy into the system, just some pumping to move solutions around slightly will create these high purity copper crystals that fall off the iron sheet and are ready for collection. And as they fall off, they expose fresh iron, which turns over the reaction on its own. On the right, you can see there really is just a plate of copper. There's no recovering that material. It's stuck fast to the scrap iron in this case. There's no valuable product to be obtained this way. So some key points here of our technology. It's operationally simple. We use ambient temperatures. There's no cathode harvesting as you typically see in electro-winning operations because the copper is falling off continuously, almost like a snow globe. You'll just have this slurry of copper crystals. It's a readily available, non-hazardous additive, blend of additives that we put into solution to create this effect as well. So it's something that we can perform on mine sites directly. And one of the key points here is that it's very fast. So in electro-winning, you're limited by the Faraday's law in terms of current potential over a surface area of your electrode. Here, it's a spontaneous redox process, so you can get very rapid copper recovery from solution, and you aren't limited to the morphology of the electrode plate. You can use, we've used scrap rebar that's just been lying around in landfills. We've been using post-consumer iron wastes, and we've been creating copper in a high purity very quickly from these copper-rich solutions. So I mentioned earlier the 20% by weight impurity of iron in the copper product from traditional cementation. Through our process, we're looking at less than 1% iron impurity. It's a very high purity copper material that we recover. Just in time for fall, you can see these crystal leaves almost you get in the static process. But we can actually control the morphology, and this is some of the developments we've made, and thanks in part to Mika. You can create different crystal sizes, different powders. We've created the rounder, more consistent, high surface area material you see on the left. And this micronized material has a wide range of applications. We actually were able to target the specific particle size distribution for certain powder metallurgy applications. So in EV batteries, components require copper metal powder, but there's a list here you can see of all the ways we can move this copper powder that's sustainably sourced into the supply chain. And we're excited to work with several partners on each of these bullet points currently, and we're developing offtake agreements as we speak for part of our, I guess, bridge seed round of fundraising. This is perhaps my favorite slide in the presentation, really just comparing our process of copper powder manufacturing to the incumbent technology. We really bypass all of the energy-intensive steps of copper powder manufacturing. Those last three in particular, the electro-winning, the smelting of that cathode copper plate into a liquid form, and the spray atomizing of that into a powder. These three are very energy intensive and typically not done on the same locations. They require transport between sites. The Destiny Copper process produces an industry-ready, commercially grade copper powder from a waste stream in a single step. So we've also turned our sights to high purity materials. We're looking at cuprous and cupric oxide. These have a wide range of applications as well. We can make them through our process. And our pilot plant is really just a simple hydromet processing facility. So we take in copper streams, we introduce scrap iron to create the copper in a single step, and then we have a water treatment facility where we recover iron powder and we treat the remaining waste stream to gray water and some recovery of our additives there. We're located in Niagara Falls, or the Greater Niagara region, Thorold specifically. This is an industrial paper mill where we have access to storage, liquid storage solutions, and we can logistically ship and receive material through rail and marine port. And you've seen this already, but this is our pilot plant where we can produce about 100 kilograms of copper per day currently. And we're starting to develop relations, as I mentioned, with industry partners to do some product validation and integrate this sustainable material into the supply chain. So thank you for your time and attention. If you have any questions, happy to chat afterwards.